Today we're going to learn how to find the integrals of the products of secant and tangent functions. And so when the power of the secant is even and positive, we're going to save a secant squared term and then convert the remaining factors in terms of tangent using our Pythagorean identities. So then would span the integral. So for example, if I have a secant raised to a 2k power, so an even power, and tangent raised to even or odd, doesn't matter, then I would first factor out two secant squares and then leave secant squared, so leave it as secant squared, tangent of n times a secant squared. And then I'd place that secant squared inside the parentheses there with our 1 plus tangent squared. And then I would let my u equal tangent, and so the derivative of tangent is secant squared, so the secant squared would cancel out, and I'm in terms of u. Everything's in terms of u. So that's when our secant is an even function. Our next kind of situation we're going to look at is when the power of the tangent is odd and positive. Okay, so we're going to save a secant tangent factor and convert the remaining factors into tangents. So again, going to tangent. So let's say I have the integral of secant to the m times tangent to the 2k plus 1 power, so that means tangent is odd, dx. So I'm going to take one of the secants and one of the tangents out. So I now have secant to the m minus 1 power. And I now have tangent squared to the k power. And then I have secant times tangent. And then I can replace that tangent squared term with the Pythagorean identity. And so I'm going to replace the tangent squared term here with secant squared minus 1. And then I'm going to let my u's be secant, and then the derivative of secant is secant times tangent, and so that extra secant tangent cancels out. Our third situation is when there is no secant term, and the power of the tangent is even and positive. We're going to convert the tangent square factor to a secant square factor, then expand. So I have a tangent to the n power, it's even power. So I'm going to take out a tangent squared. And then I'm going to convert that tangent squared term using Pythagorean identity to secant squared minus 1. Okay, when the integral is in the form of an integral of secant to the mx dx, so I only have a secant term and it's to an odd power, we're going to use integration by parts in some of our past techniques. So I have secant cubed x dx is equal to secant x secant squared x dx. So I separate my secant cubed into secant times secant squared, so I can have two terms and I can apply the integration by parts. So I'm going to let my u be equal to secant of x. And so the derivative of secant we know is secant tangent. And since u was secant of x, that means dv is going to be secant squared x. And we know the integral of secant squared is just tangent x. So plugging this into our integration by parts, we have the integral of secant cubed x dx is equal to secant times tangent of x minus the integral of tangent x times secant x tangent x dx. Okay, so the integral of secant cubed x dx is equal to secant x tangent x minus the integral of secant x tangent squared x dx. Now, we don't have a formula to meet this integral here, so I'm going to replace that tangent squared with our Pythagorean identity of secant squared minus 1, so secant squared minus 1. And so now we have minus the integral of secant cubed x plus the integral of secant x dx. Now remember, this is equal to the integral of secant cubed x dx. So this is something cool that happens with integration by parts sometimes. It's called the circular method. And so I've ended up, part of my answer here is what this is equal to. So remember, what I got here is that I have the integral of secant cubed x dx is equal to that last line we just wrote here, secant x tangent x, minus the integral of secant cubed x dx, plus the integral of secant x dx. So what you're going to do is you're going to move all the integral of secant cubed x dx to one side. So I'm going to add that second term to the left-hand side of my equation to get to the integral of secant cubed x dx is equal to secant x tangent x plus the integral of secant x dx. So let's figure out what the integral of secant x is. And so that's just one of our formulas that we know. And that's going to give us the natural log of the secant x plus the tangent x, closed absolute values, plus c. And then to solve, I'm going to divide each side by 2 to solve for that secant cubed x dx. So my final answer is 1/2 secant x tangent x plus 1/2 the natural log of the absolute value of secant x plus tangent x, closed absolute value, plus c. Oh, that's a nice one. I love it. It used our formulas for sine and secant and tangent, and it also used our integration by parts. Okay, so this integral, first thing I'm going to do is I'm going to get rid of the fraction because we don't have any division rule. So I'm going to make this a product. So I'm going to rewrite this as the integral of tangent cubed x times secant to the 1/2 x. So notice secant is to 1/2 power, tangent is to the 3rd power, so tangent is odd. So I'm going to rewrite this as secant to the negative 3/2 x, because I'm going to factor out a secant, because remember, I need to factor out a full secant and a tangent when we have a tangent squared tangent that's odd. And then that leaves me with this term here. And so I'm going to replace that tangent square with our Pythagorean identity, get everything else in terms of secant, except for that secant tangent I factored out. So doing a little algebra here, I'm going to let my u be secant of x. And so we know the derivative of secant of x is secant tangent. So that cancels out those terms I factored out. That's the reason that formula works, that you factor out that secant tangent term. So using u sub, I have u to the negative 3/2 times u to the squared minus 1. And then this secant tangent at dx becomes du. And so that's the same as the integral of u to the 1/2 minus u to the negative 3/2 du. And now I just integrate each of those terms. So it gives me 2/3 of secant to the 3/2 power of x plus 2 secant of x to the negative 1/2 power plus c. Okay, number 7, we're going to find the integral of secant to the 4th 3x times tangent cubed of 3x dx. So I got secant to the 4th and tangent cubed. I'm going to factor out a secant squared. So I'm going to rewrite that secant to the 4th as a secant squared of 3x times tangent cubed of 3x times by our secant squared that I factored out of 3x. Okay, then I'm going to replace the secant squared term with our Pythagorean identity of 1 minus tangent squared of 3x, and that's going to be times by tangent cubed of 3x, which of course is times by secant squared of 3x. Okay, so multiplying these tangent terms together, I get tangent cubed of 3x minus tangent to the 5th of 3x, all times by secant squared of 3x dx. Now I'm ready for u sub. I'm going to let my u equal tangent of 3x. Remember, the derivative of tangent of 3x is going to be 3 secant squared of 3x. And so I can replace all my tangents with a tangent of 3x's with u. And I can replace my dx with du divided by 3 secant squared of 3x. And so the secant squares cancel out. And then I'm left with du over 3. So I can factor out that 1/3, and I have 1/3 the integral of u to the third minus u to the fifth du. That's something easy we can integrate. So I have 1/3 times 1/4 u to the fourth minus 1/6 u to the sixth. And then now let's go distribute and go back to our original value of x. So distributing that, I get u to the fourth over 12 plus u to the sixth over 12 over 18, which remember u is tangent. So I got tangent to the fourth of 3x over 12 plus tangent to the sixth of 3x over 18 plus c would be my indefinite integral for this problem. All right, let's try a definite integral. So number 8, we have the integral from 0 to pi over 4 of tangent to the 4x dx. So I notice I have tangent to an even power. So there's no odd power. So I'm going to rewrite that tangent to the fourth as tangent squared times tangent squared dx. And then I'm going to replace that tangent squared with the Pythagorean identity of secant squared minus 1. And so I have tangent squared x times secant squared x minus tangent squared x dx. I'm going to break up the integrals. In our first integral, we can do u sub and let u equal tangent of x. And so my du would equal to secant squared x dx. So that first integral becomes u squared du minus, I'm going to have to use Pythagorean theorem here. So I'm going to replace tangent squared with secant squared minus 1 dx. And so I have 1/3 u cubed minus tangent plus x plus c. Now let me go back to the original value here. So I have 1/3 tangent cubed of x minus tangent of x plus x. And now remember, we're going to evaluate this from 0 to pi over 4. So replacing pi over 4 in place of tangent, I get 1/3 minus tangent of pi over 4 is 1 plus pi over 4 minus, so we know the tangent of 0 degrees is 0. And so all our terms are 0 there. So combining like terms, I'm just left with pi over 4 minus 2/3. Okay, so in this problem, we have the integral of secant x divided by tangent squared x dx. Okay, this doesn't fit any of our patterns because we're going to have a negative exponent if I move that tangent up. So I'm going to do the technique where I turn everything in terms of sine and cosine. So I can rewrite secant as 1 over cosine of x. And I can rewrite tangent of sine squared over cosine squared, but when I change my division to multiplication, I flip and multiply. And so what I have here now is sine squared, sine to the negative 2 times cosine of x dx. And so I can just do u sub with this. I can let u equal sine of x. So du is equal cosine x dx. And so this becomes u to the negative 2 du is our integral. And we just integrate that. So that's going to be negative u to the negative 1 plus c. And so that's going to be negative sine of x to the negative 1 power plus c. Or 1 over sine of x plus c, which we would have simplified that. Remember, 1 over sine is cosecant. So our actual answer is negative cosecant of x plus c. Now notice all of these powers, the angle inside the trig functions were all the same. Now this is where the angle inside the trig functions are different. Okay, so I'm going to take the sine of one function times the sine of another function. So the key is we're taking the sine. So two sine functions multiply together. So it's going to be 1/2 the cosine, and then I'm going to subtract my two angle measurements minus the cosine of adding my two angle measurements, close parentheses. Now if I'm changing function, I take a sine of one angle times a cosine of another angle. My formula is going to be 1/2 sine of the difference of my two angle measurements plus the sine of the sum of my two angle measurements. And then if I take a cosine times a cosine, different angle measurements, it's going to be 1/2 cosine of the difference between the two angles plus the cosine of the sum of the two angles. And that lets us work when we have different angle measurements. So here in number 10, I have the integral of sine of 5x times cosine of 4x dx. So I have different trig functions, sine and one's cosine. And so that's me. I'm going to use my second formula where I'm going to have the sine and it's going to be added. So I got 1/2 of my sine of the difference, so 5x minus 4x, going to give us x, plus the sine of the sum, 5x plus 4x, which will be 9x. So you can skip this step and go straight to this one. So that's 1/2 of sine of x plus sine of 9x. So I can distribute that integral. So it's going to be 1/2 the integral of sine of x plus 1/2 the integral of sine to the 9x dx. And the integral of sine of x is negative cosine of x. And the integral of sine of 9x is negative cosine of 9x over 9. So our final answer, distributing the 1/2, is negative 1/2 cosine of x minus cosine of 9x over 18 plus c. And that's what you do when the angle measurements are different.